Right. So thank you very much. Thank you very much to the organizers for the opportunity to be here today, presenting my work. Today, I'm going to talk about something that we published in June this summer together with Yichuan Li, a postdoc from Max Planck in Munich, and with Eran Palti at Ben Gurion University. So, let's start by say some words to introduce and motivate my topic. The other things I presented this paper, basically, I already start by mentioning this property of string theory that, to my opinion, is one of the most important, which is basically the possibility provided by the theory to calculate, to make computation of the vacuum energy. So this property is kind of super important because it allows us to relate the cosmological constant to other observables, other quantities describing the vacuum geometries or the compactification more generally. So given this general context, let me say that I will focus mainly in my talk on those vacua which are the most under control in the context of string theory, which are AdS vacua. So given AdS vacua and given this very nice property to be able to calculate the cosmological constant, it is kind of natural to wonder if there are some universal properties, universal feature, which characterize the vacuum energy of AdS vacua in quantum gravity. So this is a perfect question for the Swampland program. And in fact, there is a nice and interesting conjecture, which is usually called in the Swampland community AdS distance conjecture, which has been formulated some years ago in 2019, and it basically consists in this. So let's start by, as usual in Swampland, the Swampland program, to considering a quantum theory of gravity, and suppose it to put it on AdS. Then the claim is around the existence of an infinite tower of states, which become lighter and lighter in the mass, in the limit, in the regime in which we take the magnitude of the cosmological constant and we send it to zero. Okay, this is, of course, a universal statement. It's super general. And of course, when people formulate, when these people formulated this conjecture, basically was having in mind many examples in string theory of AdS vacua in which this statement is realized. But of course, we know that in physics and more generally in science, a correlation between two facts does not mean a causal relation, right? So in some sense, it is super important to start from the general statement of a conjecture and try to develop a bit more formally the idea behind it to understand if actually the conjecture makes sense or not, at least in the unique example of theory of quantum gravity we have at the moment, which is string theory. And another reason of this kind of work is motivated by the fact that, in particular, this conjecture in the last year has been used in many situations, and in particular, I would like to mention the dark dimension scenario, which rely in a strong way on this particular claim. So it is kind of interesting to understand a bit more deeper if the ideas of these statements actually works. So right, let me just give some very basic tools I will need to do this kind of work concerning the AdS conjecture. So okay, we know that in compactifications we have moduli spaces, right? We have moduli fields which capture the IR regime describing the low energy regime of our AdS vacua. And for example, let me be very concrete. Let's consider some compactifications of, let's say, type 2a or type 2b over a Calabi-Yau, and we can wonder about volume variation of the Calabi-Yau, right? This is exactly the equivalent of introducing a volume modulus. So people usually do in these cases is take the parameter describing the volume of the Calabi-Yau, letting this parameter to take some dependence over the external space, and then do the compactification, calculate the action, for example. And then we will have a new kinetic term appearing in the low energy theory, in lower dimensions. And then the coefficient multiplying this kinetic term is kind of super important because it allows us to introduce a notion of metric over the space of variations of the volume of our Calabi-Yau. So more generally over the moduli space. So now, given this metric, we can introduce even connections, curvature, and also integral quantities, like, for example, a notion of distance. So we can take, for example, two AdS vacua characterized by two Calabi-Yaus, one with volume V1, the second one with volume V2, and then we can introduce a path within the moduli space connecting these two realizations, and then calculate the distance exactly using this very nice formula. So all these things are super well defined. People worked on these things for many, many decades. And in this context, we have a nice claim, a nice statement that have been formulated 20 years ago, which is usually called distance conjecture, that basically puts some bound on how much the moduli spaces in a EFT can vary, right? So basically, when we go at infinite distance, this distance conjecture basically tells us that there should exist always a tower of states in our theory which become massless when we go at the boundary of the moduli space. So, okay, as I told you, this is just initial tools. Everything is well defined. So where is the AdS conjecture? Well, the AdS conjecture starts by a very, very simple consideration. So let's take an AdS vacuum, which is captured by some EFT in lower dimensions. So the idea is, okay, but when we go in the UV, when we go to higher dimensions, actually string theory does not make any distinction between variations associated to the internal space, which are the moduli space ones, to other kind of variations, like, for example, variations associated to the external space, to the AdS geometry itself. So the idea is, okay, if you wanted to introduce a notion of distance over the space of variations associated to some family of AdS vacua, we should include not only variations associated to the moduli space, but we should include all the type of variations we can perform over our vacuum. So this is the idea. And just to be more concrete, let's do an example. So we know that AdS in any kind of gravity theory appears as a one parameter family of solutions of the equations of motion, right? So we can start every time in gravity, taking a unitary AdS geometry and make a binary scaling, introducing a constant parameter sigma. So this binary scaling basically connects AdS solutions with different radius, so with different volume. So we know that the volume of AdS is basically the vacuum, it's vacuum energy. So we always have just an example like this manifests the fact that we always have variations, the possibility to variate the volume of AdS and variate the vacuum energy without introducing any notion of moduli space. So the question is, how can we introduce a notion of distance just by starting to this kind of simple variations that we can always introduce in gravity or supergravity and so on? Well, here we don't have all the nice mathematical structure we have in the literature regarding Calabi-Yau. So we can proceed by analogy, like we start with some AdS solutions parameterized by a parameter, let's say lambda, and we can suppose to make a variation over lambda. So we can suppose that our parameter takes some dependence over AdS coordinates. So if we stop a bit for a second, this is kind of crazy, right? Because we are not solving anymore the equations of motions. We don't have any more AdS. But in this way, you are basically going off shell from our geometry. And off-shell, we can imagine to derive the Einstein-Hilbert action, which now is an off-shell action, and it is uniquely defined by a kinetic term, a new kinetic term associated to our parameter, which now is a modulus. So what we would like to do is take the coefficient multiplying this kinetic term and call it the metric over the space of variation, let's say lambda variation. And from this metric, we wanted to introduce a notion of distance. So just before starting to do some examples, let me just recap. We have two AdS vacua with different vacuum energy. So the idea of the AdS conjecture is to introduce a notion of distance between them. And this notion of distance has to be generalized with respect to the usual notion defined over the moduli spaces, in the sense that we always at least have one contribution to the space of variation of our vacua, which is the contribution I showed you associated to the variation of the volume of AdS itself. And then the idea is that we have to include all the other possible variation we can do. I call them K prime. So if we can do that, and if the result that we obtain is positive definite, then we can formulate a generalized distance conjecture in which we put, instead of the previous distance, our new distance with all the variations. And this distance is exactly given, relate the mass scale of the tower of states to the vacuum energy itself. But this is not a given fact. We have to show that. So for example, let's start to consider the most simple one, the value scaling. So we take AdS in any gravity theory, and we take value scaling. So we suppose that sigma now takes some dependence over AdS. Now we go off shell, we don't satisfy the equations of motions anymore. So this is a super simple calculation. Let's say, okay, now let's calculate the Einstein-Hilbert action. So we can use just the formula of differential geometry. And in this way, we obtain a sort of off-shell action with a kinetic term for sigma. This is just a very easy calculation. So now what about the coefficient? Well, it turns out that the coefficient is negative. So this is kind of very crazy result, because I started this talk by saying, okay, we wanted to see if the idea behind this conjecture makes sense. So I tried to do the most simple calculation one can do, introducing the most simple variation over the space of AdS vacua. And the result is a negative definite metric. That means an imaginary distance. Well, this is a kind of surprising, not so surprising result, because if one think a bit about it, and go back in the years when people was trying to study the convergence of the path integral in Euclidean quantum gravity, they were exactly finding this problem, which is and you were calling it the conformal factor problem. So when they were including the conformal modes in the calculation of the action in the path integral, they were reproducing actions with a wrong, let's say, wrong sign in front of the kinetic term of the conformal modes, which was making the action unbounded from below. So this is basically an obstacle that we have. So given the AdS conjecture, I told you, we always have to include this external volume variation of AdS. But the crucial statement of this Swampland criteria is to say, okay, we have to include them, but we have also to include all the other possible variations. So our hope here is that if we take some concrete examples in string theory, so the other contribution could compensate this negativity produced by a very deep issue that people was encountering in quantum gravity even before string theory. So let's try to do this in very simple examples. So let's consider Freund-Rubin vacua, for example, in M theory. So in the classical limit, these are described by 11-dimensional solutions characterized by one single continuous parameter. So external variations are fixed in terms of internal variations, and which are in turn fixed in terms of flux variation. We have only one parameter, which is fixed in terms of variation of the vacuum energy associated to the vacuum. So it is a very, very simple and clear situation. So for example, we have AdS4 and AdS7, the most easy case. Let me recast them in a more compact way, in this way. And yeah, in this situation, I included two new parameters, tau and alpha. So these are over-determined, right? Because if I take this geometry and I plug it into the equations of motions, these parameters will be fixed each other. But I wanted to take them separately to see the different contribution to the distance. So let's consider, we consider variation of the AdS volume, and we produce an ill-defined result. So let's see if we include internal volume variations. So let's suppose that our tau becomes a function over AdS. This is just the volume modulus, and the calculation, even in this case, is very standard. Just by use some standard compactification formulas, we obtain a new kinetic term with a positive contribution to the metric over the space of variation associated to the spheres. So now we have the hope that the extra dimensions could compensate the negativity coming from sigma variations, right? So now the situation is we are going off shell in two directions. One is variating the external volume, and the other one is variating the internal one. So how can we sum up the various contributions to the distance? Well, our idea is to impose the equations of motions also when we are off shell. So also when tau and sigma are functions, not only when they are constant. So in this way, basically, we boil down the off-shell action to a single action in sigma, basically, in which we sum up the various contributions. And we see that now we have a new contribution associated to the extra dimensions. So what about the equations of motions? Well, in the case of Freund-Rubin vacua, we don't have any scale separations. So tau is equal to sigma. But here, I just for playing with the formula, I included also a parameter to see the more general case in which our metric describes a scale-separated vacuum. So first of all, let's see the results. So if we plug the numbers within this formula, what we obtain is a positive result for AdS4 and AdS5. So this is already a very nice result, just including the contribution of internal directions. Some of the metric over Freund-Rubin vacua becomes well-defined, but we see that, for example, for more heavy vacua like AdS7, still we have a negative result. And I tried also with more interesting geometries like the DJKT, in which we have scale separation, we have also dilaton. It's a kind of more complicated, and we obtain a negative result. So first of all, let me remind, this is a partial result. We don't have still included the flux variation, but we can already say something, for example, that there is a correlation between the possibility of introducing a well-defined positive metric, and so a distance, and scale separation. So if we take this parameter A and we take it very small, which means strong scale separation, it seems that our metric over the space of variations becomes negative. So now I'm not saying that positive metric is equivalent to absence of scale separation. I'm just saying that there is a very interesting correlation, and we still have not studied it yet in detail. So now, as I told you, we haven't included all the variations. So let's focus on this AdS7 situation in which we have a negative result. We have still fluxes. So just to show you, fluxes, you see they depend also on the parameter characterizing the variations of the vacuum energy of the vacuum. So they contribute to the distance. So to manage flux, to manage the contribution of the fluxes, we found, okay, we have to be more creative. This computation was not standard at all. So what we try to do is, okay, first of all, we introduce a parameterization for AdS, which makes the calculation simpler, which we have chosen the Poincare patch, in which AdS is basically written down as a foliation of Minkowski and a radial coordinate Z, let's say. So in Freund-Rubin vacua, of course, we can always introduce a gauge potential, right? So a function whose derivative reproduces exactly our Freund-Rubin flux. So why we need this gauge potential? Well, we have our gauge flux, our flux parameter. So when we do a flux variation, we go off shell with respect to the flux, which means that this parameter has to be dependent, take some small dependence over AdS. So when we take the external derivative, in this way, we produce a deformed flux by a new derivative in alpha. And I point out that this derivative depends only on the holographic coordinate. And this is very interesting. It is something that still we have not understood completely, but this is a very interesting fact. Yeah, given this deformed flux, we can calculate the flux action, right? So we derive the flux action, and what we obtain is a well-defined kinetic term for the flux variations, and then a very ugly vertex term, linear derivative, which basically does not allow to define any notion of metric, of distance, anything. So yeah, first of all, the calculation is kind of is very subtle. For example, for electric vacua, one also have to introduce boundary terms, but these are kind of technical things. The crucial point is what we do with this guy. Well, in order to solve this issue, basically the idea we found is this, and it's basically raising up an ambiguities in the procedure I was presenting to you right now. So I started with an AdS metric of this type, and I say, okay, let's take sigma, which is the AdS radius, let's say, and let's gauge sigma, basically. Let's give to sigma some dependence over AdS. So now, let's look at this metric, in which we introduce a sigma 1. So if sigma and sigma 1 are constant, this is actually, again, AdS. This is super easy to see, just reparameterize that. But if sigma and sigma 1 are not constant anymore, the geometry, the off-shell geometry that this reproduced by this metric is highly non-equivalent to this one. So which is the right off-shell variation we should perform? Well, we don't know actually, but we know that in this situation we produce something that is not work. So let's try to see in this other situation. So again, we come back and calculate the Einstein-Hilbert action. And the interesting story is that we reproduce exactly the same results as before, plus a new linear term in sigma 1. So our hope is to use this linear term of shell to eliminate the linear term which was produced by flux variation. So, but in principle, we don't know if we can do that or not. There is no rule in principle that allow us to do this. Well, the idea is, as I told you, is, okay, how can we wanted to always to reduce the off-shell action to a one-parameter action, because the family of vacua we are studying depend only on one parameter. So let's take the equations of motions. So in this situation, the equations of motions are only identified by two conditions. One, the first is basically associated to the absence of scale separation in Freund-Rubin. And the second is a condition we fix the flux in terms of the geometry, basically, the volume of the external and of the internal manifold. So if we solve this condition, we basically observe that sigma 1 is not fixed by the equations of motions. So in some sense, we have the freedom to choose sigma 1 when we are off shell, when these guys are functioned. We have the freedom to choose sigma 1 as we want. And of course, what we do is choose sigma 1 exactly to be related to flux variations. So in this way, if we make this choice, actually we compensate, we eliminate exactly the ugly term we had in the off-shell action, and we reproduce a perfectly well-defined quadratic action for our variation. So now we have three relations. We solve them together. So we obtain a solution depending on one parameter, sigma, which basically make the off-shell action to boil down to a unique kinetic term in which we have summed up all the possible contribution to the metric that we're calculating. And these contributions are, the first one is the negative one, the conformal factor problem. Then we have the contribution coming from the extra dimensions. And then we have a new contribution coming from the flux. So just to finish, we just plug inside this formula the numbers. Like what we do is, okay, with AdS4, AdS7, and also AdS5, we see that we obtain perfectly positive definite numbers. And yeah, here I translated basically this notation of metric over AdS variations to the notation of the distance conjecture. I calculated the exponent appearing associated to the mass scale of the tower of states. And we see that these exponents are smaller than these blue ones. And these blue ones basically were those ones calculated by these people that found a universal bound starting on the exponent, starting only from moduli space variation. So it seems that when we include this AdS variation, volume variation, actually the mass of the tower of state go to zero slowly than in the other situation, in the previous situation. So this is our result. Let me just summarize quickly. Yeah, I try to develop a bit the notion of distance, or calculate the distance between AdS vacua in string theory, starting from the very, very simple examples of Freund-Rubin vacua in 11 dimensions and in 10 dimensions. Our procedure, yeah, I admit it, is super involved. It is subtle, but the nice property is that it's rigid. So we don't make very strong assumption at the beginning, but we end up with a single number. And this number is fixed, can be positive or negative. And for our luck, the number we produced in the case of Freund-Rubin vacua turned out to be positive. And we consider is a very, very nice result. So yeah, now there are many work in progress, and what, at least to my opinion, the most interesting thing is develop a bit more this procedure to try to study flux variation in JKT and try to see what we produce in this with scale separated vacua, which for phenomenology is for sure more interesting. So thank you very much for your attention.
Thank you, Nicolò. Are there any questions? Yes, please, Daniel.
Yeah, hi. Just to understand, did I understand correctly that you're treating the fluxes as continuous fields in your approach? Is that what you're doing?
Yeah, the idea is we take a solution of the equations of motions. We take a solution of the equations of motion. Okay, so when we go in the UV completion, of course, the flux is quantized, as well as this quantity associated with the radius of AdS. These are all quantized quantity. What we do is take variations over the sets of quantized quantities. And these variations, yes, are continuous.
Yeah, so exactly. So in order to get these kinetic terms, the kinetic term contributions for the fluxes, seems to me that you have to introduce additional fields which are not really there in the actual solution. So I just, in the actual theory. So I'm just wondering how physically meaningful this approach is.
Okay, I actually don't know. Well, for the metric case, it is something more understandable, right? Because
yeah, this I understand, the metric variation. That I understand. What you said about the conformal factor problem. I'm just worried that you are treating discrete numbers as fields, as continuous fields.
These are, look at this discrete number as vacuum expectation values of some variations that you can perform. it is a small perturbation in which you don't satisfy the equations of motions anymore. So you're allowed basically to go everywhere. So of course, when you evaluate back, because you wanted to calculate the distance between two flux configurations, which has discrete numbers identified by, two set of discrete numbers. So the important thing is that when you go back on shell, when you satisfy again the equations of motions and you evaluate your variation to discrete vacuum expectation values. But here I am taking these deformations, which are basically, they don't satisfy the equations of motions. So I cannot reply you. I'm not certain regarding if they make sense or not physically, but this is actually what people do usually in physics when they wanted to study variations of some quantity, right? So you take some quantity and you supposed to variate with a small perturbation that given quantity. I have not convinced you.
I don't know. I'm not sure, but thanks for the answer.
Yeah, no problem.
Okay, very quick question, Jesus.
Hi, Nicolò. Thanks for the talk. You have at the end these gammas that you show that are lower than the one of the sharpen distance conjecture. Can you approach this bound of the sharpen distance conjecture by modifying your anti-de-Sitter, or it is fixed? I mean, can you like make bigger your gamma? Or how can you do this?
No, but I don't see the reason why it shouldn't be bigger than that. Because in some sense, these variations I'm considering are different from the moduli space ones.
So Nicolò, sorry, just to because I had also the same question, but are you suggesting that when you are in a AdS background, this parameter gamma can be lower than the bound that they found in this paper of 2022?
Yes.
Okay.
Yes, this is the result that we have.
Okay. Okay, thank you.
Okay.
Thank you, Nicolò, again. And we have to move to the next speaker, but there will be time for discussions after if you need that.